Let's now take a look at an example which has a dependent source. In this particular case, the circuit has a dependent voltage source. However, the same basic idea applies if we had a dependent current source. Quick review on our dependent sources. Of course, we can easily distinguish them from our independent sources by the shape. So in our schematic, our dependent source is going to be a diamond shape, whereas our independent source is going to be a circle shape. The other key characteristic of our dependent source, as the name implies, is that the value depends on some parameter elsewhere in the circuit, some voltage or current. And so we see here we have this current I naught defined in the top left. So that current is going to directly affect the value of our voltage of this source. And so you might be wondering, when is that actually applicable? And we'll see later on in future classes how we can use this idea of dependent sources to help us model more complex devices such as transistors. So in this particular example, what we're wanting to do is to use mesh analysis to find the value of that current I naught. And so what we're going to see is that the approach is ultimately the same. The only difference is we're going to need another equation because we have that dependent source. So only difference is we need one additional, let's see if I can write that a little bit better. So one additional equation for each dependent source that we have in the circuit. So a key thing to note here is that we are going to need one equation for each of our dependent sources. So in this case, we see that we have three meshes, and we note that our mesh currents are already defined for us. So we can say M number of meshes equals 3. So we know we need three equations. But in this case, we have a dependent source. So I'm going to say plus 1 dependent source means that ultimately we're going to need 4 equations to solve for this system. And so what we're going to see is that fourth equation related to our dependent source is typically going to be pretty simple. Okay, so let me copy our circuit down here, and let's go ahead and jump into doing our analysis. So let's start with mesh 1. And so I'm actually going to show you a slightly different way so we can do inspection, and I've made reference to this in a previous video, but basically what this is going to do is to allow us to directly jump to that final sort of simplified equation with the terms collected. So let's take a look at how we do that. And of course, if you want to see more details, you can look in the notes, and I have sort of more detailed steps written out, or you could ask me as well. So we're looking at mesh 1 first. And I'm not going to explicitly do the KVL, but instead what I can say is we notice that we have this 20 volt source, so I'm going to go ahead and say 20 is equal to, and we also have, and actually let me put that on the other side, so we'll come back and we'll say equal to 20 at the end. But what we see here is we have our 4 ohm and our 2 ohm resistor. So both of those are of course interacting with I1. We're in mesh 1, so we know that should be positive. So 4 plus 2 gives us 6 times I1. We notice that the 2 ohm resistor is what's interacting with our I1, or our mesh 1 rather. So we're going to have a minus 2I2. And so the reason that is a minus sign is because we see that our I1 is going downward and our I2 is going in the opposite direction. So because they are in the opposite direction, that's why we have this minus sign here. And then similarly, we note that we have our 4 ohm resistor is shared between mesh 1 and mesh 3. Again, I3 is going in the opposite direction of I1, so I'm going to do minus 4I3. And again, at the end here, let's bring back that equals to 20. And so you can see how that was much quicker to get to the final equation, as opposed to if we go back and think to the first way we did this, we defined voltages, we got those voltages in terms of the currents using Ohm's law, we collected terms, so we've gotten rid of all those steps, and once you get more comfortable with mesh current method, you can come directly to this final step. But of course, there's no problem with going through the earlier steps explicitly if that makes more sense to you. Okay, so let's do a similar thing with mesh 2. So over here in the bottom right is our mesh 2. We'll deal with that voltage source at the end, but ultimately we need to remember that this is just a voltage value. So kind of just treat that 10 I naught the same as we would 20 volts. It's just a number, and we'll address that later when we're talking about our extra dependent source equation. But for now, let's look at our resistor value. So because we're in mesh 2, any of our I2 terms should be positive. And I'm going to write my I1 term first just so we can have I1, I2, I3 in all of our equations in the same order. So as we just said, our I1 and I2 are in different directions. We note that they're both going through this 2 ohm resistor. So we can say we're going to have a minus 2 times I1. Now, if we move on to our I2 equation, we note that I2 is going through both the 2 and the 8 ohm resistors. So 2 plus 8 is going to give us 10 I2. And again, that's going to be positive because we're in mesh 2. And then finally, we see that our current I3 is interacting with this 8 ohm resistor. I2 and I3 are in opposite directions through that resistor. So we can have minus 8 I3. And we would say that that is equal to this voltage over here, which would have been negative. We moved it to the other side, so we'd have 10 I naught. And again, we're just treating this value as if it were a constant voltage like we have for our independent source. Now, what I'm going to do is, of course, I naught is a variable, so I'm going to go ahead and move that over to the left side. So I'm going to put this over here as minus 10 I naught, and we have then, of course, let me just shift that a little closer, minus 2I1, and of course we need to get rid of it over here on this side because we've moved it, and set that equal to 0. So I'm going to come back and adjust my mesh 1 equation just a little bit, and the reason is I want to have an I naught term here as well. Of course, we didn't have an I naught, so I can just write I naught times 0 plus these other things. And that's going to be, I want to have that there so that when we go to plug this into our matrices, we can just do that sort of directly, and we don't have to be adding things in our head or saying, oh, I know I have a 0 I naught. We can just explicitly look at these equations and see that. Okay, so our final mesh is mesh 3. And so let's do that one by inspection as well. So let's come up here, and now we're looking at mesh 3. We note that we do not have any sources, we just have the 3 resistors. So same type of procedure as we did with our other 2 meshes. We notice that this 4 ohm resistor is the one that I1 is interacting with, the only one in mesh 3. And as we've stated before, I3 and I1 are in different directions in that resistor. So we're going to have minus 4 times I1. Similar thing for I2, we're now looking at this 8 ohm resistor. I2 and I3 are in opposite directions, so we'll have minus 8 I2. And then finally for our I3, of course it's going in all 3 of those resistors, and because we're in mesh 3, the I3 term should be positive, so 6 plus 4 plus 8 gives us 18. So we're going to have plus 18 I3. And we had no voltages, so that's equal to 0. We did not need to incorporate that I naught, we'll get to that here in a second, but we still want to include it in the equation, so we're going to do a similar thing as what we did up here for our mesh 1 equation, and we can say 0 I naught. So we just added it in just for completeness there. Okay, so as we can see, now we have 3 equations, and we actually have 4 unknowns. So 3 equations, got ahead of myself there, with 4 unknowns, and so what that tells us is that we need one more equation. And so that's sort of what we expected from the outset, because remember we said that we need 4 equations, 3 of them from our mesh currents and 1 additional one from our dependent source. So this is sort of just confirming what we knew from the beginning, and of course our unknowns are I naught, I1, I2, and I3. So the process for getting this final equation, we're going to call this our dependent source constraint equation. And so as I alluded to earlier, this is going to be a relatively simple equation. So our dependent source constraint. So we come back up to our circuit, and what we're doing is we want to look at our dependent source. We want to ask ourselves, what does it depend on? In this case, I naught. We find where I naught is defined in the circuit, and then we want to relate that. So we want to relate that I naught term to our mesh currents. And depending on the circuit, it might just be 1 mesh current, it might be 2 mesh currents. This dependent variable, instead of I naught, it could be a voltage, so we might have to relate that to mesh currents and resistors. But we want to get everything in terms of our mesh currents. In this case, it's very straightforward because we can see that our I naught is actually just equal to I3, because of course here is our I3 coming along this mesh, so we can see that's equal to I naught. So again, the dependent source constraint is typically very simple. So we just have I naught is equal to I3. So at this point, what we could do pretty easily if we wanted is we could just take that I3, or I naught equals I3, and we could substitute it into this mesh 2 equation, and we get minus 10 I3, and we just combine that with our other I3 term. What I'm going to do is I'm going to go ahead and leave this as 4 separate equations, just so you can see the process if that fourth equation for our dependent source constraint is a little bit more complicated. So what I'm going to do is rearrange this. So I'm going to say I naught plus 0 I1 plus 0 I2 minus I3 is equal to 0. And so now what we can do is we can take these 4 equations. So let's label these. So 1, 2, 3, and 4. And we can put these in a matrix. And so let's go ahead and show that. So we're going to have I naught, I1, I2, and I3. And we have for our first row in our coefficient matrix that comes from our first equation, so 0, 6, minus 2, minus 4. In our second row we have minus 10, minus 2, 10, and minus 8, and that comes from our second equation. Third equation gives us 0, minus 4, minus 8, and 18 for our coefficients. And then finally, our dependent source constraint equation gives us 1, 0, 0, minus 1. We invert that, and we multiply by our constant matrix, which is 20, 0, 0, 0. And note, we just have the one term from our independent voltage source. We don't have any terms from our dependent source in this constant matrix. And so if we plug that in, we're going to get values for all 4 of those currents. So we get negative 5, negative 3.214, and these are approximate values, negative 0.9643, and negative 5. And because we had all of our values up here in ohms and volts, this is going to be in amps. And so of course the current that we're interested in is I naught. That's what we were asked about. So we can see that I naught is equal to negative 5 amps. And as sort of a quick sanity check, just to make sure we didn't make any errors in our math or filling in the matrix, we can see that our I3 is equal to negative 5 as well, which we would expect from this final dependent source constraint equation here.